finishes, we will be ready to go. Okay. The major announcement I have to make, and I think that most of you, if not all of you, are in good shape here. The ones that are here. Those that are not here, I can't say for all of you, but the Vice President last week, I saw an email that he sent, and there's supposed to be a script that I read to you, and I wasn't at a printer at the time, so I couldn't print it, and I haven't had a chance yet today to print it, so I haven't printed it, but I'll tell you the basics of it. Now, it's a little embarrassing because I think most schools would be way ahead of here. In fact, most of you are from other schools, right? When would you have had to pay if you were enrolled in summer term at that school? First day, first week?
You had to do paid.
What's that?
So you had to do what?
To have paid.
Before.
Yeah, or even before, okay? Now, here, he just sent it, or I just saw it last week. He may have sent it the week before, but I just saw it last week. That as of 5 o'clock today, if you haven't paid, you're going to be removed from the roll. Okay, so I don't know why they do this, and they never let us know when that date is. It's just all of a sudden you'll pop up with an email. Okay, after this, no one. So if you have not completed your payment, please get on the horn with somebody, see if you can get it in process. The people down in the cashier's window, that's our business office on this campus, our financial services, if that's where you need to go through. But you need to contact someone and tell them that yours is in the process. And if it's not in the process, you need to get it in process really soon. But I think I'm preaching to the choir here. I think all of you, I believe, are paid, but it's been a while since coming out. Did the attendance over the weekend, and I don't remember which ones had asterisks by their names and which did not. But this week is not really drop dead, but he's going to do it then, and then usually he gives students a chance to go and cry or give excuses or whatever, and then he lets them in anyway. So, and then it's a pain for us, but it's okay. I'd rather have you than not. Okay, but anyway, did want to let you know that. One other minor thing, I don't know if this will affect any of you or not. Generally, on Tuesdays and Thursdays, my office hours are 10 to 12 in the morning and 3:30 to 5:15 in the afternoon. I don't have hardly any office hours on Monday and Wednesday. Tuesday, Thursday, that's what they are. However, Tuesday tomorrow, as soon as I get out of my 3:30 lab, I've got to head over to the Birmingham campus and screen applicants for a biology position. So I will not be available in any office anywhere unless I finish that screening before 5:15, and then I'll go to my office on the Birmingham campus, which is in the B building, B122. So if you are looking for me tomorrow morning, I'll be here 10 to 12, but not tomorrow afternoon from 3:30 until 5:15. Sorry about that. Okay. Any questions on anything we've covered so far? All right. We're beginning today. Now, the slide section numbers are not quite the same as the ones in the book. In the book, we're in Objects in Equilibrium, and this is 4.6.1. Okay? And an object either at rest, sitting there, not moving, or moving with a constant velocity is said to be in equilibrium. Now, does that mean constant speed? Constant speed, if it's changing directions, it is not a constant velocity. So, constant velocity means straight line motion, constant speed, no change of direction. Okay? Or something completely at rest. Those are said to be in equilibrium. The net force acting on an object is zero. If it's in equilibrium, since it's at a constant velocity, the acceleration is zero. If it's at rest, the acceleration is zero. So that means the net forces acting on the object is zero. Now, there's one thing that's a little bizarre about this equation you see here, I hope you're familiar with the sigma notation. That's the summation, summing all the forces together. Usually this has a counter like I or J or something like that. For I equals 1 to 17 or whatever, then this would be F sub I, sorry. Adding all those forces together. But because forces are vectors, this is actually the zero vector, okay, which is a rather bizarre concept in itself, because most of the time a vector has some magnitude in some direction, right? Except for the zero vector. It has no magnitude, and of course it has no magnitude. How can it be going in any direction? But they still write this as a zero vector, and that's why it's bold like that. But the net forces are zero, okay? Did everybody get that? Okay. It's easier to work with the equation in terms of the components. In just about everything that you're dealing with vectors, it's easier to work in terms of the component. So do the sum of all the x components of all the forces. That's got to be 0, and the sum of all the y components of all the forces, that's got to be 0 as well. Now that could be extended to 3 dimensions. You just then have one more, sum of all the forces, the z components of the forces has to be 0 as well. A 0 net force does not mean the object is not moving. It means it's not accelerating. Remember my earlier example of an airplane flying at 500 miles per hour, constant level flight, straight line flight. That's the equilibrium. The net forces on it are 0. Sure, gravity's pulling down, but the lift is pulling it up. The engines are pushing it forward, but air resistance is pushing it back. The net forces are 0 if it's not accelerating. And if the net force is 0, then it won't be accelerating. That's what we mean by being in equilibrium. It may have a velocity, but it has 0 acceleration and 0 net force. So here are a few examples. I have a couple other pictures on the side of the book in your margin. But I'll just refer to them. In fact, let's do it before we even get here. These are pictures that refer to Quick Quiz 4.8. Now, if you have a text, look on page 101 at that. If you don't have one, see if you can look on with someone who's close by. Okay, consider the two situations shown in the figure. Okay. The first figure is a guy pulling on a spring scale. I'll just say it's attached to a wall. So let's say that wall over there had a very solid attachment on it, a hook out there. I put a spring scale, a fisherman's scale, or something like that, and pulled on it, okay, and held it at some distance out here, okay, and but just stood there holding it, okay. There's situation 1, in which there is no acceleration. I'm holding the scale out there. I'm pulling with a force of magnitude F on the spring scale attached to the wall. Okay? Now, the second figure there shows me pulling and Will pulling in opposite directions on the spring scale. And just pulling, and we're at a standoff there. Okay? Page 101. Is that what you're looking for? Section 4.6. Huh? No, 4.6. Yeah, I'm sorry. Actually, in the text it's 4.6.1. In the slide it says 4.5. It's not. It's 4.6.1. Okay? The second of these figures here, the second one, are two people. Will and I are pulling. and we're pulling with the same force we did before. I did before, and he's pulling with that as well. But he's pulling in the opposite direction on the spring scale. So he's the fish, and I'm not, whatever. Okay, so there's the scenario. I'm pulling against the wall, or I'm pulling against Will. Okay? In both cases, the man or the men pull with a force of magnitude F. Now, the question is, the reading on the scale when I'm pulling on the wall greater than, less than, or equal to when Will and I are pulling against each other? We're both pulling with force F when he's pulling. What's the reading on the scale? Is it when I'm pulling on the wall greater than, less than, or equal to when we're pulling against each other? Make a guess. Topic 4.8. Second? C. Very good. Equal to. Okay? Just because I'm pulling with a force F and Will's pulling against me with force F, that doesn't add to B to F. The reading on the scale is still whatever it would be if I was pulling against the wall. Because we're at equilibrium, I'm pulling, see, the wall pulls against me, remember Newton's third law, or Will's pulling against me. It doesn't matter, the reading on the scale is the same. Very good. Now we're ready for the second one here. A traffic light weighing 1 times 10 to the second newtons, which basically is 100 newtons, okay? They use the scientific notation to indicate 1.00, 3 significant digit thing. Where would I indicate that on this diagram? Okay? Is it showing up anywhere here at all? Not really. There is F sub G. That's the weight, that's the force that the gravity is pulling downward on the traffic light. That is its weight. Okay? So this is 100 newtons. Well, let me get my pen activated. Darker color. 100 newtons. I think that's what it was, wasn't it? 1 times 10 second, right. If we did it here, this would be little w, which is equal to mg. Okay, this would be 100 newtons. Same here, and okay. Now, this hangs from a vertical cable tied to 2 other cables that are fastened to a support, as shown in this figure here. Okay? The upper cables make an angle of 37 degrees, as you see there, and 53 degrees, as you see there, with the horizontal. Find the tension in each of the 3 cables. In other words, find T1, T2, and T3. Okay. Now, things to note here. A traffic light weighing 100 newtons hangs from a vertical cable tied to other 2 that are fastened to the surface. Okay. They make these angles, and basically the implication is it's hanging there. It's not moving down, it's not moving up, it's not moving right or left, it's hanging there. Still. Okay? So what do you reckon in that force on that? And what we're interested in a little bit, this, the net force on this is what? 0, because it's at rest. Remember, we said that earlier. It could be moving at a constant velocity. It's not. It's just hanging there at 0 speed, 0 acceleration. It's just hanging there. So what does that tell you right off the top about T3? If the weight downward is 100 newtons and its net force is 0, the T3 has to be 100 newtons. Okay? Now, what I'm writing right now are magnitudes. Okay? And I think that's all they're looking for. Let me read again. Find the tension in each of the 3 cables. The light is the traffic light is pulling downward on that cable, but these are pulling upward. So I would say tension, and especially since they have it italicized here, as opposed to vectors, that means all they're looking for is the magnitude here. Okay. Now, you can get that from the sort of like a free body diagram of the light. Gravity's pulling downward, the tension's pulling upward. There's only 2 forces. It's in equilibrium. They must be equal or opposite. Gravity downward is negative. The T3 is upward positive. Upward positive. So that would be positive 100 newtons there. Here they just talked about magnitude, so 100 newtons is fine. Okay. Now, that gave you the tension in T3. That's the easy one. All right. Now, what we have to do is figure out the tension in T1 and T2. Now, don't go by lengths. That doesn't really contribute much to it. It's forces here. Okay? Now, what you have to do is to break each of these forces, tensions, into horizontal and vertical components. Okay? So, I'm going to introduce, if I could draw a straight horizontal line, it would be something like that. What angle would you say this was? Say again? 37, because it's alternate interior angle. So this is a 37.0 degree angle, and this would be your 53.0 degree angle here. That 0.0 is really ugly. Okay. Now, break each of this tension into a horizontal and vertical component. Let's call the horizontal component here T1 horizontal, and the vertical component here T1 vertical. Similarly over here, break this into T2 horizontal and T2 vertical. Okay? Okay? All right. Now, what can you tell me about this figure now? Remember, T3 is here 100 newtons. Okay. I just want you to note here, T3 is pulling up on the light, but down on this junction. T3 is a tension, basically pulling both ways. Now, notice the cables aren't stretching. They're not changing, they're just hanging there. That's one of the requirements. So what can you tell me about the net force on this dot right here? 0. It's not moving, it's not accelerating. The net force on that is 0. We know the downward force here is this T3, 100 newtons downward. So what could you tell me at least qualitatively about 2 other components I've shown on the board? T1 vertical plus T2 vertical has to equal T3, right? the magnitudes do. Because these are pulling up, this one's pulling down. Again, don't let the lengths fool you. It's the force. So those two are up, this one's down. Now you could write that as plus plus with a minus and equals 0. So I found it just as easy to say T1 vertical plus T2 vertical is equal to T3 vertical. Understanding this one's down, those two are up. Okay? So let me write that. T1 vertical plus T2 vertical is equal to T3. And we know what that is, 100 newtons. Well, what is the breakdown of T1 vertical? Especially since you know this angle right here is 37.0 degrees. What is that vertical component? The vertical component of this angle is the opposite component, and this would be your hypotenuse, because there's your 90-degree angle. So what trig relationship relates to the 37 degrees here, the opposite of the hypotenuse? Sine. Okay? So that would be T1 vertical would be T1. We don't know what it is, but that's what we're looking for. T1 times the sine of 37.0 degrees plus, give me the other side, T2 vertical here. What would that be? And by the way, I guess I skipped over something. The sine of 37 degrees is T1 over T, right? Okay? That means multiply both sides by T, T1, and that's where you get T1 vertical is T1 sine 37. Plus, and what can you do on the other side? Say yes, okay. Plus T2 times the sine of 53.0 degrees. The sum of those has to equal to 100 newtons. Okay? Now, how about the horizontal components? Sure enough, this dot here is not moving up or down, nor is it moving right or left. It's stationary. It's fixed. It's at rest. So what can you say about those two tensions? T1 horizontal and T2 horizontal. Anything? Second?
The net force here.
Yeah, the net force is 0. In other words, T1 horizontal must be the negative of T2 horizontal. In other words, they're equal but opposite. So the magnitudes are equal and opposite. So let's write that. And what is T1 horizontal in terms of that angle and T1 that we're looking for? Second? Cosine. T1 times the cosine of 37.0 degrees is equal to T2 times the cosine of 53.0 degrees. The magnitudes are. They're equal and opposite in directions, so the plus the minus is equal to 0, so add the minus on both sides and you get equal to each other. All right. Now, there's a couple ways you can do this, and it's completely up to you. But I think the easiest way is to take this bottom equation and write the T1 in terms of everything else, or the T2 in terms of everything else. I really don't care which way you go, but in other words, solve this equation for either T1 or T2. Which one you want to do? T1 or T2? Pick one. T2. Okay? Solve it for T2. So what we're going to do is divide this side of the equation by cosine 53.0 degrees and divide this side by cosine 53.0 degrees. Okay? That goes out here, and that gives us another measure of T2. That's what T2 is. So let's take that and plug it into the first equation here, this equation. I'll write it here. T1 times the sine of 37.0 degrees plus, and instead of T2, I'm going to write T1 times the cosine of 37.0 degrees over the cosine of 53.0 degrees is equal to 100. Okay? Now guess what, team? We have an equation in, the only unknown here is T1. The rest of the numbers are either known or palpable. Okay? So if you want to, you can factor out the T1. And that would then be sine 37.0 degrees plus cosine of 37.0 degrees divided by cosine of 53 degrees is equal to 100. Okay? So then what I would do is divide both sides by this thing. Okay. I'm just going to wipe it out here and divide it here. Sine 37.0 degrees plus cosine 37.0 degrees over cosine 53.0 degrees. Okay? So if someone has a calculator, it's messy, but it's quite doable. Okay? Type in 100 divided by, open parentheses, sine 37 degrees, be sure you're in degree mode, plus cosine 37 divided by cosine 53, close your parentheses, press equal, see what you get. $100 divided by, open parentheses, sine of 37 plus cosine 37 divided by cosine 53, close parentheses, equal. Now, by the way, remember, every time you do a sine or a cosine, it opens its own parentheses, so you have to close those too, around the 37s and the 53s. But the one that you open, you be sure you close too. Anyone got an answer yet? Anyone? Uh, 51.8, is that what you said? Huh? Yeah. Okay. Again, let me, you follow and see what, if you got the same thought. 100 divided by, open parentheses, sine 37. Now you have to close the parentheses for the 37. Plus, cosine 37, you got to close that parentheses. Be sure you're in degree mode. Do that first. But after that, you divide by cosine 53 degrees, close that one and then close the overall one, then press equal. Okay. Sierra, right? Okay. And Brianna, right? Good deal. We're doing the example 4.9 on the bottom of page 103 in section 4.6 of topic 4. I guess we got more coming in. Okay. Is it Embry? Okay. All right. Has anyone else come in whose name you've not heard me call? Okay. For those who did come in since I initiated this, I've got to say something else because the Vice President's requiring it, and so I have to say it. For any student, and be sure you pass this along among friends or fellow students, classmates, or whatever. If you have not completed payment for the summer term, you need to contact someone before 5 o'clock if possible to let them know what your plans on doing that are. Because he said if a student has not completed payment by 5 o'clock today, they will be removed from the roll. So please, if you or someone you know, if you have a friend that takes classes on Tuesday, Thursday, or with you in some other class, this one, another one, and they have not completed payment for the summer, you please let someone know what your plans are, because they're going to remove those after 5 o'clock. Now, if you're already in the process and it comes through and stuff, you have to, I think, go see the Vice President and show to him what has happened and stuff like this. I think he lets you back in. It's not a bad thing, it just is tedious, so please get it done today if possible. Sorry about that. Okay, now my memory is just about everybody in the class has paid. It's mostly the students who have not shown up that have not paid. That's understandable. I just don't remember if any of the others of you who've been here frequently have not paid. So you have to know that. Check it out. Okay. Did anyone redo this and get a different answer? That's not an unreasonable answer you got, but it's not the answer they got in the book. Got the same thing again? Okay. Let me watch you. I know my writing stinks. Let me watch on the calculator. Here is Darius, right? Okay. Now I have to say this every time someone new comes in. Vice President last week said it, or I saw it last week when he sent the email, that anyone who has not completed payment by 5 o'clock today will be removed from the roll. So if you or anyone else you know who's enrolled this summer hasn't done so, please do something. Let the business office or financial aid office know what your plans are for completing payment. Otherwise, we don't know. So let's see. Display type. Okay. Yeah. Okay. Then I'll divide it that side. Okay. Open parentheses. Okay. Sine 37 degrees, and you have to close that in parentheses. Plus cosine 37. That divided by cosine of 53. What is that? Another close equal. Okay. Oh, wait. Sorry, I was looking at... Nope. That was supposed to be T1. All right. Second. Okay. What we got so far is T. They did it the other way, but it's still okay. They got T2 is equal to cos. Let me see if that's right. Oh yeah, that's what we got. Cosine 37 over cosine 53. All right. Okay. And then that we plugged in where T2 was above. Oh, sorry about that. We left off the sign. Sorry. Yuck. We got T1 sine 37 plus, and T2 is T1 cosine 37 over cosine 53. Then that's times, here we go, sine of, sine of 53. Yeah, I knew we were missing a sign in there. Sorry about that. Okay. Then when you factor out, I know this is messy. Okay. This is sine 37 plus cosine 37 times cosine 53 divided by cosine 53 times sine of 53. Okay? So then when we're dividing by, this also has sine of 53 degrees. Okay. So let's read that again. Sorry about that. I thought I had it in there, but I didn't. Okay? 100 divided by, open parentheses, sine of 37. Be sure you close that. Oh, be sure you open parentheses before. 100 divided by, open parentheses, sine 37, close that one out, plus cosine 37, close that one out, times sine 53, close that out, divided by cosine 53, close that out, and then close out your big one, then press equal. Second. Let me find it. 60.1, is that what you said? 60.1 newtons, that is your T1. So T1 is 60.1 newton. Okay. Sorry about that. I left off the one thing. Now, how do you get T2? Plug it in right here. Keep that 60.1 or whatever, however many digits you got there for T1, and then multiply that by cosine 37 and divide it by cosine 53, because T2 is equal to that. Anyone get that yet? Anyone? Anyone got an answer yet? 60.1 times cosine 37 divided by cosine 53. A little louder? They got 79.9. That sounds close enough. 79.9 newtons. Okay? Now, does that seem reasonable that T1 and T2 added together is more than T3? Yeah, because this is vector addition. Some of this 61 that you're doing here, some of it's in this direction, some of it's that way. Here, the 79, some of it's this way, some of it's that way. This part and that part basically cancel each other out, so those aren't contributing anything. It's just this part and this part is equal to that part, and that does work out. Okay, sorry about missing a term there. Now, let's move to the next illustration, which is this one. Sled on a frictionless hill. Okay? A sled is tied to a tree on a frictionless snow-covered hill, as shown in this figure here, the A part. Excuse me. If the sled weighs 77 newtons, how can I indicate that somewhere on this figure? The sled weighs 77 newtons, 77.0 newtons. Where and how would I indicate that? Weight is always what direction? Weight is a force, which is a vector quantity. And here we have Ryan. Okay? How would I indicate the weight of that sled? 77 newtons. Where this weight is a vector, it's a force, it's pointing somewhere. Where does the weight point? Straight down. Okay? So this would be your Fg equal mg, which is 77.0 newtons. Very good. Here I would indicate something very similar. Weight downward. Okay. Find the magnitude of the tension force, T, which is exerted by the rope on the sled, and that of the normal force, N, exerted on the hill, by the hill on the sled. So here's your tension force, T, right there. That's one thing we're looking for. And the other is the normal force, which is up this way, perpendicular to that. And this is the second thing we're looking for. Okay? Now, there are the three forces we know. Weight downward, normal up, and tension up in the other direction. This normal is not straight up, it's with the hill. Two of the three forces we're looking for are perpendicular to each other. Tension force up the hill, normal force perpendicular to the hill. Got to be perpendicular to each other. So that makes perfect sense to set up your coordinate system along that axis. Up the hill is, say, the x-axis, and perpendicular to the hill is the y-axis. That throws the force, the weight, to having components. Even though it's pointing straight down, we're not using straight down being y, we're using perpendicular to the hill being y. So that means we have to break the weight force into a component that's perpendicular to the hill. This is mg perpendicular, and it'll also have a component down the hill, which is mg parallel. Is that okay to call them that? Weight down, perpendicular to the hill, or down the hill, which is parallel to the hill. Okay? And guess what? The weight downward, perpendicular to the hill, is going to be that normal force, and the weight parallel down the hill is going to be the tension force. So if we can find those two, we got it knocked. Only thing that we got the little bit of a problem on is I know this is a 30-degree hill, okay? But I've got to translate that to mean what is the angle in this triangle, okay? Well, if this is 30 here, theta is 30, what is the angle right here? Say again? Someone said something. Well, guess what? What is this angle down here? That's 90, because downward and horizontal, that's 90 degrees. Okay? So if that's a 90-degree angle, and these two are the other angles in a right triangle, what is true about them? Say again? They what? The sum of all three adds to be 180, and since one of them's got to be 90, then the sum of the other two has to be 90. So if this one's 30, what's the other? 60. Okay? 60.0 degrees. That's that angle. But that's really not one of the ones either. But between down the hill and perpendicular to the hill, that's obviously 90 degrees, right? So that means this angle right here is 30. Exactly. And this one down here is 60. Okay. So, I know this is a little messy here, but they've shown it here. This angle right here is 30 degrees. They didn't show this to be 60, but it is. Okay? Well, if that is your angle theta, and you can choose either one of them, if that's your angle theta, then the downward component here of your force, of your weight, is what relationship? This, by the way, this is your 90 now. Okay? I'll draw over here on this because this is perpendicular to the slope, this is parallel to the slope, so that's a 90-degree angle. So that makes the side over here, the downward pull here, to be what relationship to this angle and the weight that we know. The weight is your, these are the 90 degrees here, what is the weight? That triangle? Right triangle? You got two legs and a hypotenuse, which is the weight here. That's the hypotenuse. So therefore, if we're talking about the downside here, the down the hill side here, parallel side, relative to this angle, the sine of this angle theta will be the opposite of our hypotenuse. So that would be the downhill thing, component divided by hypotenuse. So therefore, multiply the hypotenuse by the sine of 30, and you get this component right here. Does that make sense? Can someone tell me what the sine of 90 is? I mean, sine of 30? I think you said it. What was it? 0.5, 1/2. So that means if the sine of this angle is 1/2, that means this side is exactly 1/2 of the hypotenuse. We told you the hypotenuse, so guess what? You know the downhill side. And what is it? Half of 77? And this, by the way, is that normal, the tensional force. This is 38.5 newtons. Right? Does that make sense? Okay. Now can you tell me the normal force? two ways you can do it. You know the hypotenuse, and you know one leg. You can use Pythagorean theorem to tell you the other leg, which has to be the same as the normal force. Or you could say this leg here has to be the relationship between this angle, theta, this leg, and the hypotenuse. This must be the adjacent side. It is the adjacent side of that angle, and it's the cosine of 30 is equal to this component divided by the hypotenuse. In other words, the hypotenuse times cosine of 30 is equal to that side. To me, that's easier than squaring and taking square roots. So let me say it again. And here it is. It's right here. It's the weight times the cosine of this angle is equal to this leg here. And that leg is the same as the north. Okay? So 77 times the cosine of 30 equals, say again? I heard something like 10. Okay. Just look. Oh, there it is. You said 66.7. Okay. Okay. I thought I heard a 100. I thought it can't be. Okay. So this is 66.7 newtons. Okay. Yep. They got 38.5, which was the easy one to do, and 66.7 is the other. All right. There is another quick quiz. I don't think we have a picture of it. Nope. Okay. This again is a frictionless thing, snow and ice, whatever. Here we have a woman, and I don't draw women well, you know, don't draw anything well. A woman here sitting on a sled, being pulled by a guy. Okay. Pretty ugly, huh? Okay. Being pulled by a guy, okay, on a toboggan, shown in the figure in your book. If you got your book, look at page 103. It's a lot nicer than mine, okay? Now, for the woman being pulled forward on the toboggan, is the magnitude of the normal force is this force pushing up on the sled, toboggan, equal to, no. Okay. A part is equal to the total weight of the woman plus the toboggan. B greater than the total weight. C less than the total weight. D possibly greater or less than the total weight, depending on the size of the weight relative to the tension on the rope. Whatever that means. You tell me, is the normal force here greater than the tension on the rope, less than the tension on the rope, the same as the tension on the rope, or it could be greater or lesser depending on that? I think that's what the question. No, I'm sorry. This is the normal force. Okay? It was the weight, mg, weight is equal to mg, and that's down like this. So it's the magnitude of the normal force greater than, equal to, less than, or it could be greater or equal depending on the tension of the rope. Sorry about that. What do you think? Let's see what it says. Woman being pulled forward on the toboggan is the magnitude of the normal force exerted by the ground on the toboggan equal to the total weight of the woman plus the toboggan, greater than the total weight, less than the total weight, or possibly greater than or less than the total weight, depending on the size of the weight relative to the tension in the rope. Let's throw that last one out because that doesn't make any sense at all. Okay? So, equal to, greater than, or less than is the normal force equal to, greater than, or less than for this one. A, B, or C. A is equal to, B is greater than, and C is less than. Any guess? Can't hear? B, which is less than, right? No, greater than. Okay? Actually, it's C, which is less than, and here's why. Notice the guy is pulling, the tension on the rope is this way. That has a horizontal component, but it also has a vertical component. So these two components, the normal force plus the tension vertical, add to be the weight. So the weight is greater than the normal force because the tension. Now if he were pulling perfectly flat, then it would be equal. If he was pushing perfectly flat, these two would be equal. But since he's pulling upward, then the normal force is less than this one because this component of the tension force is lifting it. If he was pushing downward, like if she was sitting on the back of it, he's pushing down forward, then the normal force would be greater because the downward push would have a vertical component downward and the weight would be downward. So that would be greater. The normal force would be greater. But in this case, it's less. Let's see, make sure they got it right in the back. And this is 4.9. And 4.9 is indeed C, which was less than. Tell you what. Okay. Any questions on that? All right. Now, there's several more really good examples in the text. If you want me to do any of these, I'll be glad to do it. But what they are moving toward are multiple objects. Any of these examples, I have example 4.9, moving a crate, 4.10, a runaway car, 4.11, weighing a fish in an elevator, and 4.12, sliding hockey puck. Any of those you need to see? Okay, I'll take that to be a no, but I'm not getting much feedback. Let's look at two-body, and what the slide set says is multiple body problems. This is 4.7 in the text. It's still listed as a 4.5 here. Okay, when you have more than one object, okay, multiple objects, the problem-solving strategy is applied to each object somewhat separately, okay? You draw the free body diagrams for each object. We really did that, if you remember, with the traffic light. We dealt with the traffic light first and then the connector that's above the traffic light. You apply Newton's laws to each object and you solve the equations that you get from those objects. Okay? Here is their classic example. They love to give this, and this is Atwood's machine. This is example 413, top of page 107. All right. Two objects, M1, that's the round object here, and M2, that's the square object here, with M2 being greater than M1, okay, are connected to by a light, that means light in mass, inextensible cord, that means it doesn't stretch or contract, and hung over a frictionless pulley, as shown in this figure. Both, sorry, both the cord and the pulley have negligible masses. Okay? Find the magnitude of the acceleration of the system and the tension in the cord. Okay? We want the acceleration of the system and the tension in the cord. Okay. Now, there's a fair amount to do here, and they don't give you any numbers. Okay, that's sort of a sad part here, but it's doable without numbers. All you know is M1 is the smaller mass, M2 is a heavier mass. Okay? Sorry about my throat. It's really giving me pain today. All right, what they did is draw a free body diagram of the Sat-With machine. Okay? First, settle on M1. What forces does M1 have out on it? Any? Sure. Gravity's pulling it downward. And the cord is pulling it up. Tensile force is pulling up. M2 has the same tensile force upward because this is a non-extensible spring. It doesn't stretch or shrink. Negligible mass. So sure, pulling has negligible mass. So sure, the net force acting on this is the tension upward and the mass down, the weight down. Okay. Now, these two tensions are the same. They've got to be. It's the same spring. Pulley is massless, frictionless, so there's nothing that's being lost or given away there. So the tension on the spring is the same. T, this T here is the same as that T there. What's different is M1G is less than M2G. Because they told us the mass of 1 is less than the mass of 2, so therefore multiplied by the same constant. The forces would be different. Okay. Now, sorry about my throat. They list here the accelerations of these two masses as well. Mass 1 must be going upward. Mass 2 must be going downward. Now notice these aren't velocities, these are accelerations. Okay? Now, the acceleration 1, let's get it in terms of forces. Okay? The net force on M1 is the mass times the acceleration on mass 1, and this is the difference between these two. That would be T minus M1G. Okay? The force, oh, I forgot. No, I'm sorry. Yeah, M1, that's right. The force on M2 is M2A and that's equal to mg2 minus, okay, sorry. The signs here to get to be a little tricky. It's M2G minus the tension upward. And I haven't broken down the tensions into two different tensions. The magnitudes are the same. Now, sure, one's up and one's down, and that kind of stuff are actually both the tensions are pulling upward, okay? One's with the movement and one's against the movement, okay? So the sum of the net forces here is so the net force downward is this force minus this force. Oh, one other thing. Sorry about this. This acceleration downward here is exactly the same as the acceleration upward here. The strings aren't stretching or shrinking or snapping or anything, so the accelerations are identically the same. Okay? So the directions are opposite, but the magnitudes are exactly the same. Okay. So the net force of the system is equal to the mass times the acceleration of the system. Okay? And that's what they're looking for here is the, so what we've written here is, and they've written it in terms of magnitudes, so I wrote vectors because I had vectors here. M1A1 is equal to T minus M1G, and M2 is equal to minus T plus M2. Okay, so we've got that correctly written as well. I just put the MG2 in front. Now, and I'll have you note that this is M, they label it M2, I mean A2, but it's really, in the text, they write it as A1, because those are exactly the same. Substitute A2 is equal to minus A1 in here, and you've got it. Okay? Now, the whole system is moving with the net force on the system is M1 plus M2, that's the net mass of the system, times A1, because it's all moving with that acceleration, okay? And that's equal to the sum of these forces, which is the top plus the bottom, okay? And that would be, I'm going to start with the bottom, M2G minus T plus T minus M1G, okay? The T's go out, and what we have then is A1 is equal to M2G minus M1G okay, divided by the M1 plus M2. Okay? And you can factor out the G. I'm so sorry about my throat. M2 minus M1 G divided by M1 plus M2. Okay? And that's exactly what they get here. Now, that's the first question. What is the acceleration of the system? Well, the acceleration of A1 is the same as acceleration of A2, just in the opposite direction. We let the signs account for that. And that gives you, and looking for that, solving for that, is dividing the total mass of the system from the difference in the net forces. Okay. Simplifying that. Now the second question is, what is the tension in the string? I think that's what they show it here. Okay. Find the magnitude of the acceleration of the system and the tension in the cord. Okay. Well, the tension in the cord, you can do either one of two ways. I find it easier on this one. The tension in the cord will be the mass 1 times that acceleration that we just found minus plus m2g. Okay? So, okay. So T, and either one of them will work this way, is equal to your M1 times this acceleration we just determined, M2 minus M1 over M1 plus M2 times G plus M1G. Okay, I think yeah. Okay. And what you can do is factor out the M1 and the G, and what you have left is M2 minus M1 over M1 plus M2 plus M1. No, plus 1. Sorry about that, plus 1, because you factored both of those out. And I don't know if there's a... Yeah, they do another couple steps here. I'll bring it up here. Well, number one, they don't factor out the M1. I don't know why, but they don't. So let's see what we got. Factoring out the G only, which you do have in both cases here. It's sort of tedious, but it's doable. Okay, you have M1, M2 minus M1 squared plus M1. Now, I'm just going to leave it like that for right now, over M1 plus M2. Okay, and this is all multiplied by G. Okay, well, we need to get under the same denominator, so we'll multiply this by M1 plus M2 and multiply this by M1 plus M2. 2. Okay, that's pretty ugly. I can't read up there, so I didn't know where I was writing. It's really ugly. M2. Okay, so let's multiply these together. M1, M2 minus M1 squared plus M1 squared plus M1 plus M1 M2 divided by m1 plus m2, and all that's multiplied by g. Well, notice here the minus m1 squared and plus m1 squared disappear. These two add together, so that gives you 2m1 m2 over m1 plus m2 multiplied by g. Okay, so that's your tensile force. Okay. Now, I find these usually somewhat of a pain in the neck to do, especially because the answer I gave at the beginning is the same as this one, but it just doesn't look the same, so you had to do some more manipulation to get it there. And this is a little bit simpler looking for, but it's just getting it the way they want it. Okay? So your acceleration was this, and your tension force is this. Acceleration, of course, this is a mass, difference of two masses plus sum of two masses. That's going to be a fraction that's smaller than g, because it's the difference over a sum. So it's going to be a fraction, but the units here cancel out, so you have the same units for acceleration as acceleration due to gravity, which is great because you want that. Over here, however, you need to have an extra mass left here. Well, this is a mass, and this is a product of masses, so one of the grams or kilograms or whatever goes out, but you still have the other one left. And the tension is now greater than the units are right. Mass times acceleration gives you a force. So it does work out well, but it's just sort of a tedious problem. You have to keep up with each thing and then your total acceleration. Okay. Now, before we get into forces of friction, which is wait a minute. Oh, goodness gracious, I forgot. We already did the forces of friction. Remember, we followed the book, not the slide set. The book and slide set changed the orders on them. And did I make sure that we didn't skip anything? Boy, I can't remember, because this was so, they rearranged the order in the book. Yeah, we did. I think we did all of it there. So we've already done this, forces of friction. Okay? Yeah, I remember doing that, and this, and this, and that, and that. We looked at the coefficients. Did we do this problem? I can't remember that. We did. Fantastic. Okay? Did we do this problem? Connected masses. I don't recall doing that one, and I don't think it's in your book either. Let's see if it is. Because it's really a two-body system. There it is. Okay. We didn't do this one. This is page 108, example 414, connected systems. Okay. Again, the okay. All right. In your text, it has a special subsection on the system approach. We just did the two-body problems using each individual body. 4.71 is the system approach, and I'm not sure there is a slide on this one. Yes, it is. Here it is. System approach. Treating the system as one object allows an alternative method for a check. And here we use only external forces. The tension is not an external force. It's an internal force. It's on both of them, remember it pointed opposite direction. Yeah. The mass is the mass of the system, not the individual masses. Now, this approach cannot tell you anything about the tension on the rope because it's only dealing with the externals. So it can't tell you anything about the internal forces, but it can tell you about the acceleration of the system. So, for instance, that last problem we did, Atwood's machine, one of the questions was, what's the tension on the rope? The system approach could give you nothing in that sense. Okay? So, here is your connected object problem. And here's what it is. A block with mass M1, there it is, of 4.00 kilograms. So M1 is 4.00 kilograms. Okay, again, this is the example 4.4, top of page 108. And a ball with a mass of 7 kilograms. So this ball mass of 7.00 kilograms. Okay? Are connected by a light string. When they say light, that means neglect the mass. Okay? Light string that passes over a massless, frictionless pulley. Okay? That doesn't mean it really is massless, but it has such a very light mass, it's not going to affect the problem any. Okay? As shown here. The coefficient of kinetic friction between the block and the surface is 0.3. So mu sub k is equal to 0.300, and that's a dimensionless quantity. Does anyone know why? Because that mu is a ratio of two forces, okay? And that's one reason, but it's just a dimensionless quantity, 0.300, okay? Find the acceleration of the two objects and the tension on the string. Number one, you can't find the tension on the string using the... Okay. We'll do it separately first, then we'll come back and check it. But all we can check is the acceleration of the system using the system approach. Okay? So that's what we're going to do. All right. Now, we need to treat each body separately, and that's what the free body diagrams are doing here. This first, mass 1, the table is pushing up with a normal force N. Okay? Gravity is pulling downward with a force of M1G. Okay? You also have a frictional force pulling this way, mu sub k times the normal force. Okay? You also have the tension of the string pulling that way. So those are all the forces acting on the block, on the table. And that's how they're represented here. Okay? They just said F sub k, but I told you what F sub k was. Mu sub k times that normal force. Okay? Now, time out. Is the block either flying off the table or sinking through the table? No, neither. So therefore, the normal force is exactly equal to the weight. Exactly equal to. There's no net force up or down. So we know exactly what the normal force is. It's M1G. Okay? So M1G is 4 times 9.8, and that's what? Someone punch that in quickly. 4 times 9.8. 39.2. 39.2 newtons. That's also your normal force. 39.2 newtons upward. Okay? Now that gives you your force on the frictional force, because that's your coefficient of kinetic friction times the normal force. So that would be 0.3 times that. So this will be 0.300 times 39.2 newtons. And that shouldn't be hard to punch in either. What is it? 10, 11, 0.3 times 39.2. Second, 11.8. And that would be in newtons. Okay? Now we don't know the tension yet. Okay? Let's go to the second body. That's the ball. Mass of 7 kilograms. Two forces acting on it. M2G and the tension upward. Okay? Same tension, same string, everything. Okay? So, M2G would be 7.00 times 9.8. You could put 9.80 if you wanted to. And this is kilograms. This is meters per second squared. So 7 times 9.8 gives you 68 point what? 6. This is 68.6 newtons downward. Okay? All right. Now, don't make the mistake now of saying this is in equilibrium. Okay? It's not. We could say the force down is equal to force up because it's not moving up or down. The block is. Okay? We can say this through here, but because those tensions are the same in opposite direction, we can now take this minus this, and that will give us the acceleration of the system, which I think is what they're asking for, isn't it? Find the acceleration of the two objects and the tension on the string. Okay, so the acceleration of the two objects. Okay, the net force is this down minus this that way. So this is 68.6 newtons downward minus 11.8 newtons that way. So that gave us 57 newtons. Okay, the net force Fn on the system is 57 newtons, right? Okay. Divide that by the mass of the system, which is 11 kilograms. And by the way, a newton is a kilogram meter per second squared. So kilograms go out. This gives you the acceleration of the system. Okay? Which is what they asked for, I think. Find the acceleration of the two objects, yeah. And what would that be? 5.2 meters per second squared. Okay, how did they do? Yeah, they did 5.17. I thought we needed another digit there. 5.17 meters per second squared. Okay? Now they have to figure out what's the tension in the string. Well, that's not too bad, because we know the let's just go back to this ball right here, and we know its weight downward is 68.6 newtons. So m2g minus t is equal to m2 times this acceleration of the system. Because the ball's going that low, this will give you what t is. So if you multiply this acceleration, 5.17, let me clean that up so you can read it a little bit better. Okay, 5.17, multiply that by 7, okay, and what does that give you? .17 times 7. 36, 37, 38, something like that. Huh? 36.4. Say again? 32.4. No. 7 times 5 is 35. 36.2. Say again? 36.2. The difference in that is 30. Oh, you had already subtracted. Yeah, 32.4 would be the tension. That would be newtons. That should be the tension in the string. Let's see if that's right. 32.4 newtons. Very good. Okay. There's a B part. It says check your answer for acceleration by using the system approach. And basically we kind of did that to begin with. Our system, I use that to get the acceleration of the system, period. So it works out to be exactly the same. Okay. So those are connected objects. Any question on that? Now, let's go back to the friction part. Sorry, this is jumping all over the book. We talked about static friction and we talked about kinetic friction. This slide is just going to talk a little bit more about, it's really still the same two things. The other types of friction, friction between a moving car's wheel and the road, is that moving or kinetic or static? Between the wheels of the tire and the road. Even though the tires are moving, it's still static friction. Only time that's kinetic friction is if the car is skidding. If you're spinning your wheels, then that's kinetic friction. If the tire is gripping the road, then that's static friction. Okay? That's what you always want to be the case. Now, most cars these days have what they call a feature called anti-skid or something like that. You'll see.
Traction control?
Second?
Traction control?
It could be called traction control of some vehicles, right? And what that does is, well, especially when you're braking, if you start to skid, then the car automatically, even though you're still pressing on the brake, it pulls off until you get back to static friction, if you can get to it, okay? The other kind of friction you have on a car is air resistance, and that's given the big R here. So the friction of the tires on the road, the tires are turning this way, and the road, and since this is static friction here, that's pushing the car forward. So, I've destroyed this question now. Is friction good, bad, or indifferent? What do you think? Friction good, or is friction bad, or is friction can be either? Huh?
Either.
Why? Why do you say that?
I mean, I guess generally it's gonna be like it could be either of like, let's say you're throwing across the, let's say like you're riding your bike or something, you get tossed along the pavement, like you get rashed up, but
Right.
like, at the same time, you're not just gonna keep going forever. Or I don't know.
No, I think you're sort of onto something there. What's that? It kind of does.
You want to be able to walk.
Yeah, exactly. I could not walk across the room if there was a static friction between my shoes and the floor. Okay? If I'm the old cartoon thing of stepping on the banana peels, then that's sliding friction. You're not getting anywhere except falling down. So static friction is absolutely necessary here, but in your car, you want as little friction as possible in the engine, right? You don't want the metal rubbing against metal and having any friction there. So in all the drivetrain and the engine and everywhere else, friction's bad, really bad. But tires on the road is absolutely necessary. You really want to have the friction there. So yeah, you can't say air resistance, not good. Unless you're on happen to be jumping out of an aircraft, then you want to be air resistance, don't you? Catching under the parachute and keeping you from crashing into the planet below. So, yeah, they can be either or. All right. Say again? All right. That ended the section, the chapter, or at least the slides on it. And I think we did all of the quick quizzes. I believe we did. And again, sorry that this is messed up. I need to get the new slide set, and I don't have it yet. The book also has some of the connected objects. 2 blocks on a cord. And a cord. This is on page 109, example 415. Cars and frictions, we just talked about. There it was. The last slide is on page 110. And then air drag. They don't have a picture of this one, but that's Applying Physics 4.2. That does end the chapter. There's a summary here, and the summary has definitions summarized. It has, most of them anyway, it has illustrations summarized. It has some of your equations summarized. Looks like about 21 equations there. Well, they don't list them all here, but they list a lot of them. You'll have to go back in the text and pick those up. There are conceptual questions. I think the odd number answers are in the back. But the big things are the problems, okay? 4.1 and 4.2, odd numbers 1 through 17 have answers in the back. 4.3, 19 through 25 have answers in the back. 4.4, static friction forces, 27 through 31 have answers in the back. 4.5, tension forces, 33 through, not that many of those, 33 to 37. Applications of Newton's laws, 39 through, this is a big one there, 53. And two-body problems, 55 through, this is a really big one, 71. Okay? And then there's additional problems that sort of combine all those features together, any of those odds, 73 through 91. Whole tons of those. All right. Now, it's coming close to 4 o'clock, right? We started at 2, so we've gone 2 to 3:50. Yeah, it is time. Okay. Don't know what to do here. The lab is probably going to take pretty close to 2 hours, but we could do the lab, see if we can get it all done in the hour and a half we have left, and then, and if so, you can take off and go. I think you can probably finish it. It's just going to take me a little while to set up because it's sort of has a lot of little pieces to it. So you want to go on and try to do the lab, or you want to go on and start talking about energy the next chapter? Say again? I couldn't hear. I almost thought I heard someone say go home, but I'm sure no one said that. Okay, I was afraid of that. Okay. No, we're going to do one of the two. Either start on the lab or start on chapter or topic 5. Which you rather do? Let me know something. Okay, let's get started on the lab. Okay, what I'll do then is in this, here they come. Boy, right in between today. I'll go and mark Raven is here on the first part. This, no, actually the second part. Okay. And the same with Bria. Alright. I guess I'll call and mark the roll. FA is out of town, but Nick is still here, mostly. Kiara is still here. Courtney Brooks is still here. Okay. Got Raven. Shakina is still here. Charity, we still haven't seen her except the second day of class. She said she'd be here today. Courtney is here. Ambry is still here. I'll find you. Yeah, there you are. Okay. All right. I knew I hadn't seen you read. Essence is still here, wanting to go. Okay. Ryan is still here. Larius hasn't made it in today. Monique is still here. Sasha is still here. Allison is still here. Darius is still here. Scarlett's still here. Will's still here. Brianna is still here. Naya is still here. Already got Bria and Dakota still here. That's out of the way, so let's just I'm going to pause. All right. Everybody got a copy of the lab? Yay or nay? Okay. Let's see how many people we got here. According to roll call, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 divided by 6 is 3 per group. One group will have 4. Okay? So you got a 4, you got a 4. Okay, I need a group of 3 here. Group of 3 here. And a group of 3 over there. Okay. All right. 1, 2, 3. Good deal. Need 3 over on that table. need 3 on that table. Okay. Need 1 more, 2 more on that table. 1 from, we got 4 groups of 3. I need 2 groups of 3 and 1 group of, so need 1 more over there from this table or one of these tables. Come on, 2 people need to join Ryan. Okay? Courtney and Courtney. Okay. Good deal. And there are some more schools if you don't have schools. Are you joining or not? Okay. Well, no, okay. You got 3 here. Yeah, but I need 3, a minimum of 3 in each group. So you got your 3 now. One of these 2 teams, 1 person join Ryan and Courtney. Okay. Okay. All right. That was harder than I thought it was going to be. Okay. Each group should have, listen up, folks. Listen up, folks. Listen up, folks. Each group should have 1 multi-surface board. Okay? Looks like this. Good. Bingo. 1 friction block with 1 hook, and 1 friction block with 2 hooks. Now, 1 team is missing 1. This one I take right here. And what you'll do is whichever team around you finishes with the 2 hooks first, you need to share with this group over here, okay? So I found my other block, but someone had taken both hooks off of it. So 1 block with 1 hook and 1 with 2. 3 20-gram masses, okay? Some of them will look like these. Some of them will look like these, okay? And a few of them look like these. But there'll be flat discs with the 20 grams on them, or there'll be a mass like this with 20 grams listed on them, okay? So those are the 3 20-gram masses. Okay? A spring scale. These are your spring scales. Now, these are not great scales, okay? But they'll do the job for this class, okay? I will probably need to help you get them calibrated. That includes, okay? And an inclined plane, and here are your inclined planes that you should recognize. Turn them so that the team can see the scale. We'll be using these. And also loosen them up so they go up and down really freely. If they get stuck somewhere, loosen them a little more. Okay? They should go up and down very, very freely. Okay. Now, all right. You'll probably need to turn this so you'll be able to see from the outside. Fairly easy. Okay. Good deal. Got it? No, wait. This is falling apart. Okay. I think. Okay, I'm going to have to go get the replacement. This one is having some major problems. I can maybe repair that later, but not now. All the other inclined planes move up and down fairly freely. Okay. I'll be right back. Sorry about this. Okay, which team was it? Right here. Okay. Sorry about that delay. Okay. Now, it says measure the mass of each of the friction blocks in grams. Okay? Now, what you have to do before you can do this is take your scales here, and for instance, this one, it's reading right now 15 grams and nothing's on it. So what you have to do is hold that in place and force the needle to 0. Okay, now it's only reading about 8 or 9 grams. So do a little more this way. That's about 7.5. About 5. I got it, so it's right on 0 when you hold it like this. Okay? Anyone else need some help with that? Now you have to hold this and that's pretty good, isn't it? Or a little bit more. Pretty good, don't you think? Okay. How are y'all doing? A little bit more this way. I guess that's good. How are yours? Got it right on 0 or is it a little off? How are y'all? Did you get your calibration? Oh, nice. Good to calibrate? Yeah. Okay. All right. Now, let me tell you something about these scales. Okay, as you'll tell by looking at them, already gotten out of calibration. Okay. You can tell by looking at them, you're using the gram scale. You know it's goes 0 to 50 with 4 longer lines, so each of those is 10, so the little ones in between are 5. So exactly you can get to 5 grams, you can estimate in between that. So the first little mark there would be 5 grams, 10, 15, 20, up to 50. See that? You have to know how to read these things, right? Okay, you're looking at it to see what it's talking about. Okay, so measure the masses of your 1 hook and 2 hook blocks. Once you get that done, then let me know. Okay, that gives you the mass in grams. The next thing you got to do is get that in kilograms. How do you go from grams to kilograms?
Times 1,000.
Say again?
Times 1,000.
Not times. Divide by 1,000.
From grams? Oh, okay.
Yeah, you're going from a smaller unit to a bigger number, so you you divide by the 1,000. So move your decimal 3 places to the left, okay? How do you get the weight in newtons? Multiply the kilograms by 9.8, exactly. Okay? Everybody got it? So let me know when every team has finished your measuring the masses in grams, convert to kilograms, and convert to newtons. Good deal. Okay, I'm going to pause the recording just so there's not going to be so much. The two block with 2 hooks, then you pull ever so slightly. Is that 0 is? See, you can't do it if it's below 0. Got it? Get this. Set at 0. Okay. So what you do, you hold steady, and you pull ever so slightly, but you don't want it to slide. Right before it slides, then you read the maximum reading right before it slips. See what I'm saying? Okay. Okay. This is you got to have some room, like maybe over here. You got room over here. All 3 of you. Okay. Don't move any stuff over here. You need room. Okay. So all 3 of you need to get around over here. Okay. Got it calibrated nicely. Okay. You perhaps hold this. Don't let it move. Okay. Now you take the board and slide it. Okay. You got it all on the board. Okay. Slide it ever so slightly, but you don't want it to start sliding yet. You don't want this to slide, and read the maximum reading you get there. Okay? Do you see what we're saying? Do you have yours? You got the one with 2? Okay. Have you done it reading it? Okay. Then, okay, you're holding, and somebody else slide the board ever so slightly. Better to get it between 2 people than like this. Okay? And I don't calibrate it at all. That right on 0. Okay. What you need to do, you hold that steady, and one of you slide the board toward you, away from her, until right before the block slides on the board. Right before it starts sliding, read the grams there. Okay. Have y'all finished along with 2 blocks? Have you finished? Team over here. All right. Have y'all finished one with 2 hooks? Oh, okay. Okay. No, wait. Okay. When you do it for the moment you say, yeah. You have to hold that. Yeah. Be sure you're calibrated before you start. Okay. What's that? What? Okay. Okay, that looks like it's done. Okay. Now, yeah, you hold it. Okay. Wait, no, yeah. Let her do the pull. You just hold. Okay. And you pull this way until right before it slides. And you read and see the maximum it goes to right before it slides. Okay. All right. Everybody is reading or has read. Somewhere I probably left my laptop. Good, thank you. Huh? Oh, thank you. Okay, everybody is on A2 now. Anyone moved on to A3? Okay. Do the same with the mass of one block. Oh wait, I'm sorry. Place one mass on the block. Okay, now what that means, a 20-gram mass. Oh, you've done it. Okay, you're moving on that. So do the same thing with that. Everybody see that? You don't hook it to it. You place the mass on the block. Okay. And then do the same thing, and then do the conversion. So somebody has started. Was there a question? No, the one with two hooks. Yeah. Be sure you get the same two hook block, because you need the mass on that and everything. Okay. All right. Oh, and by the way, it says place one mass on number 3, place one mass on the block. What is the total mass now in grams? You don't have to weigh it again. What you have to do is just add 20 to that block. You've already weighed the block. You know it's a 20-gram mass you're adding to it, right? Okay. And keep going in that way till you do the mass for 2 blocks, mass for 3 blocks, and then when you have a place that you need to stop, let me know. What I would say, why don't 2 of you go with one group and 1 of you go with another group and watch them do 2 blocks. Then you'll come back and be a group again. 2 on 1 and 1 on 1. Yeah. All right? Yeah. Actually, why don't you get a block group of 3? So it'll be 4, 4, and 4. Huh? Yeah, go on and get there. Yeah, we'll do that. So why don't you have only a group of 4 here and 1 of them joins this one. Go on and get the numbers from. Okay? And join another group with 3. This one only has 3. So yeah, why don't you do the group of 3 over here? What's that? I don't think it ought to make a big deal of difference. If it looks way off, then use their calculations on the others. Sorry about that. I just couldn't find the 6 block with 2 hooks. Someone had taken the hooks off. All right, every time you add a mass to the previous, add 20 grams to that. Okay, then when you pull your thing, that's a measurement. You measure that. But when you add the mass, you don't have to go back and measure everything. Just add 20 grams to it. The B part, that's on the second page. And by the way, it's lab 4 on both pages. The second page says lab 5. It really is lab 4. It says place the surface board on the inclined plane and place friction blocks, and only mean 1. Okay? So either one you want to, the 1 hook or 2 hook, it doesn't matter, on that incline, and gradually increase the incline of the plane until the block just begins to move. Now, that is not particularly easy with these things because they stick. So try to do it, have it as loose as possible, and move up as slowly as possible until right at the time you see them start moving. Okay, is that what you're asking?
Yeah, well, I was going to ask you this one.
Yeah.
So the theta is the angle we take with something else, right? So if we got to move that 20 to 20.
Okay, let me, yeah,
I'm just saying, like, okay, so we do it with 2, so we'll change it. If we got 20 degrees, it would be
Right.
here. And then it'd be 10, 20. What do you do?
yeah, exactly.
These are repeats, like we did this already. Because it's saying the same thing, and we already did that for the first page.
Okay, this is the 2 blocks on top of each other.
We did that for the master gets multiple, right?
Yeah, but this is 2 blocks. This is the 2 blocks. That'd be 25 to 25.
Okay.
You see what I'm saying? Now, the first is on top of each other. That would be like this. And you can pull in one off the other. And the second time, you put like this, and you do like this. What's that? No. You wait them, just add the 2 together. You wait them separately, right? Yeah. See, once you did those 2 weights of the blocks, that's all the weights you do. Everything else you know, you use that other method. Oh, I'm recording. Sorry about that. On page 2, number 10 is stack the 2 blocks on each other. You don't have to weigh them again, just like I said before. All you have to do is add from 1A the mass of the 2 masses that you got there, and then do your calculations from there. Then when you hook one block to the block with 1 hook to the block with 2 hooks, they're pulled along. Still, you just add the masses together. All right, moving on to the B part. I'm going to try to say this loudly enough for you to hear from here. So, place the surface board, and which does it say? Paper portion. Okay. Yeah, that portion there. And you can do it either up here or down wherever you feel best to place the block on there. Okay. And then you very slowly increase. Now, someone needs to be here reading. Okay. When motion begins. So someone do it as slowly as possible. Oh, 40. Second. 43. three, okay. Yeah, you might need to do it a few times. I think what I would do is hold it from the top side. I would hold it from the edge. So yeah, and you get a good guess on that. Yeah, you see what happens. Now when you go to these others, you might have to move it. Nothing's going to be very convenient. So when you move it like that, like this, and then you do the other. So, wait. Huh? No, down the. You see, when you do that, you do like that. You start coming down. Hold it here. It's called warping. So you do this one here, then flip it over and do the other two. That way. Yes. On this one? Okay, pretty good. We block one. What you do, make it very, very slow. Very slow. And block first begins to move. There we go. It's like 42. So I'll let you do it 3 times. Do it on this surface and that one. Now, did I see y'all doing the other one? Yeah. I saw a real heavy coat there. Okay. That's right. Again, maybe it might require some coordination. I would flip this and
We take this to me. What you supposed to do?
Hokey. Hello, good. Strong. And you all know that you're reading from the bottom, that longer side, when you're doing your angle. Okay. Yeah. If you can do a good estimate, if it goes completely off, it runs out. Like they just went 46. You know, just 49. That's not good. Go later than 50. All right. Okay, I've got a question. We are really just about out of time. Has everyone gotten through the A part and you're now on the B part? Okay. What we'll do when we come in next time, I'll probably have to set up the lab again, but I won't need as many pieces. I'll just need one block, the board, and the inclined plane. So it won't take nearly as long to set up. So why don't you just pause here. You won't need your measurement because you're not doing weights anymore. All you're doing is the inclined plane. So if everyone's finished with the A part, that's A1 through 14, then it's a good time to stop, and we'll come back at the first of class. We'll meet in the classroom. I'll call roll and all that. Then we'll come here to the lab and finish up the lab, and then we'll go back to the classroom. Now, before you go, I've got to run down and get your test. She didn't have them run off before class, so let me run get them. I'll be right back.